the booklet too, how to get it back in case you lose it.
Yeah, we did that last time.
Oh, we did it, we did it. I've done it like 5 or 6 times over the past couple days, so. Cool, and then real quick, the scatter plot. Let's see, got one on. And this, I'm going quickly only because we did spend a good chunk of time last time doing this. That's the TI scatter plot. You might realize that compared to the Excel scatter plot, it's kind of lame. It's kind of lame. I mean, Excel scatter plot has labels. It's got a title. It's got axis labels, numerical and verbal. Yeah, Excel's great for this. Your last project in here is going to be getting you in Excel and making these very graphs. But the TI we have. We all have, or most of us have a TI around or some access to something that can do this. So unfortunately, it's not the best tool, but it's the most common tool. If you do need the numbers on the TI scatter plot, you can press the trace button right now, and what it does is a little spider pops up. A little spider pops up, and then you can jump from point to point, and it'll tell you the X and Y coordinates, which is hardly, I mean, the same as having axes, which is the most important thing, I think. But at least, for lack of a better thing, it gives us some numbers on the graph. Cool. And then, how to get the best fit line. The TI does it all for you. I'm going very quickly through this because it's in that booklet. The TI does a very, very good job. Boom. There it is. There's our best fit line through our data points. And if you need the equation, it is sitting there in Y1 waiting for you. So hopefully, this is calling back to your Math 95 and your previous math days when you actually would graph things like this in the TI and look for highs and lows and crosses and things like that. So 1.05x plus 33.1. Let's put the overhead back on, go over to this graph here. Same exact equation that Excel gave us. Excel does the exact same thing. I'll have you do that in your next exam. I'll have you find the best fit equations for your next exam in Excel, which is way more fun and way more probably common than using your TI. What does the 1.05 mean again? I think this was the last thing we talked about in class together. What does the 1.05 mean? It's the rise over the run, literally. Good, it's the rise over the run. Sorry, I'm putting an error even though Randall said it. It's the rise over the run, but give it to me in context.
Million people per year.
Nice. What about them, Kelly? 1 million people per year?
On average.
On average. Keep going. That's what I need. I need a little more context. 1 million people per year become uninsured. 1 million extra people, or 1 million people per year become uninsured. That's the idea of interpreting the slope in context. So you see 1.05, you're like, okay, 1.05. And then in your brain, you go, okay, that's a slope. That slope, so let's put this up again. That's A over here. So you know from your previous classes that that's rise over run. So that's rise over run. I'm sure you can see this. Well, rise, and some people call this change in y over change in x. How many of you guys did delta y over delta x? Does that sound familiar? Or is it y2 minus y1 over x2 minus... That sounds better. That sounds more familiar. Let's take that away. y2 minus y1 over x2 minus x1. That delta, that triangle symbol in Greek, whenever something changes in math or science, it's very often indicated by a delta symbol. If you talk to an engineer, they'll talk about, oh my god, the delta T is right now. When they talk about the temperature dropping, the delta T, the change in temperature. It's just a shorthand that gets used in science a lot. Nobody's ever seen that though in math? Okay, then we'll stop talking about it. Change in y over change in x. So you know that when you talk about a slope, you have to be involving both variables. And you have to be involving both units. The unit on y and the unit on x. The unit on y is the millions of people that are becoming uninsured. And the unit on x is the amount of time that has passed. So when you interpret a slope, just FYI, next week's the quiz is on the Facebook privacy policy. The Facebook privacy policy. If you look at the data, which you will, it's actually pretty conveniently linear, fun. And I'm going to ask you to interpret what the slope means. And that interpretation of the slope needs to have both the units on the y and the units on the x involved in it. 1.05 is great, but 1.05 what? Million people per year. And I like the on average. The on average is perfect, because it is on average. Kelly, go!
So for like units for that one, they wouldn't be in the thousands.
Oh, that's not units. I'm talking about the verbal unit on it. Thousands of what?
So it'd be words per...
That's what I'm talking about, like the words per time or whatever. I think it's time again, or per year. But the idea is you have to involve these words in the interpretation. Whenever I ask you to interpret a slope, you have to involve those words of the unit. Whether it's thousands or millions or billions or tens or ones, but definitely the words. Because if you just tell me the slope's 1.05, that means you can read. Yay! I'm glad you can read. But I want you to know what that 1.05 means more than anything. And it means a little over 1 million people per year more become uninsured. Fair enough? Fair enough. Ish, maybe. Getting there. Getting there. And it's an average. Who said on average? That was awesome. Thank you, Joanne. On average, yes. Because does this ever go exactly 1 million people per year? It doesn't look like. We actually went through this in class. That to there, over 2 years, went 3 million. Well, 3 million over 2 years is 1.5 million a year, right? That's too fast. Here to here went 1 million in 2 years. That's 500,000 per year. That's too slow. But it's not that it's telling us what happens over any given year. It's talking about what happens on average over the whole period of time. Fair? Yes? Maybe. Getting there. Getting there. All right. Good. Pull us back now. We left with that interpretation, and then I had a whole bunch of... I scared you with that, I think. I apologize. I didn't mean to. But we wanted to talk about... for a second. Basically, some nuts and bolts kind of problems to work on. Some nuts and bolts kind of problems to work on to make sure that we knew, now that we had this equation, because really, honestly, that equation is huge. It was huge. Because now you've got a relationship between the data, and the data's relationship is in the equation or the formula form, and now you can use that formula like any other algebraic construct. The reason you have algebra is actually, it's not just to torture students, honestly. I know it seems that way. Like, why do you have algebra classes? Well, because my dad suffered through it, and now it's my turn. And no, it actually, I mean, that's what a lot of students feel, I think, is that algebra is this mysterious thing that originated in the Middle East, and my parents got through it somehow, grace of God, and good constitution. It actually allows you to solve problems. This looks awful, yes? I look at that and I'm like, hell yeah! Because that allows us to solve a problem. It allows us to get to what is the best line without having to guess repeatedly at the solution. I'm not saying it's the best tool for everything. I'm saying it's the best tool for certain things. Much like I look at the RoboGlip pliers I have in my shop, I love those freaking things. Sometimes. Because every once in a while, I get this crazy-sized nut buried back in a rusty cavern, and I got to get in there and yard down. It's the only tool that'll work. But I don't use it to, say, change the light bulb in Max's lizard tank.
Why not?
Because it's a dumb tool to use for that. Just like algebra is a dumb tool to use for measuring the grade of roads. Yes? Stupid. You use simple arithmetic for that. You wouldn't use algebra necessarily to measure the height of a tree if you use multiplication instead. But for stuff like this, it's great. So we interpreted, okay, number of uninsured Americans under age 65. I think we did this one together last time. How many were there in 95? How many were there uninsured in 95?
35.38.
Say that again, Francis. I hear your voice. There you are.
35.38.
Say that again.
35.38.
35.38 million. So we got 35, we call it 35.4 million. Love it. How'd you get that?
I times 5.05.
Good for you. So you said, okay, I'm going to put it right here. We know it's a little out of sight here. So for the uninsured data, for this one, which I don't think I numbered, did I? No, I didn't. It's got an arrow. So number of uninsured Americans under age 65, number uninsured in 1995. Go ahead and describe your process, my friend.
Well, I think I times it by 1.05.
When you said it, what's it?
The number of years.
Good. So what number did you use?
I don't know.
So you multiply 1.05. What you're doing is you're looking at the equation, 1.05x. So 1.05, you multiplied x. What is x in this case?
Is it time of the year?
It's 5, right?
Yeah.
5 years after 1990 is 1995. So you're going to say, okay, y is going to be the number of uninsured I'm looking for. I'm looking for that number. Which means I take the 1.05, which is my rate of change, and it tells me each additional year I pick up that many more uninsured. So I'd have to go 1.05 plus 1.05 plus 1.05 each year, but that's why we invented multiplication. So we can stop adding all the time. That's the whole reason multiplication. So 1.05 times 5,
Plus the 3.
and that's the starting point, yes? In 1990, it's thought that there were 33.1 million uninsured Americans, and each additional year after that, we picked up 1.05 more. And that's what this is showing you, yes? We start here, and each additional year picks up 1.05 more million people. There, excellent. So what's that, 5.25, yes? Check my math on this.
Yes.
33.1, that's going to be 38.35, there we go.
Wait.
Make sense? So 38, roughly 38.4, about 38.4 million people are uninsured under age 65 in 1995. And you could totally crunch it out that way. That's the beauty of having an equation. You can crunch it using an equation. Yeah, Tammy?
Wouldn't you just go on the table and look for...
That's the other way you can do it. I'm not saying there's one correct way to solve a problem. That's just one way to do it. But we also looked at that table feature that your TI has last time, which is an additional way to do it. And here's kind of a general guideline or a general rule. If you have an algebraic equation like this, where you've got y as a function of x, if you have the x and need the y, go straight to the table. It's the easiest way to get the y that you need. It's the easiest way. So grabbing your TIs, I think this is the very last thing we did in class on Monday. Grabbing your TIs, just go straight to your table. Second graph. And it's left over from yesterday, or from Monday. You input in 5, and out pops 38.35. There you go.
Why do you have, for some reason on here, it has all just nice neat numbers? It doesn't...
That's because it's set up to be auto, not ask. We can check at the break and I can fix it for you so it's at ask. Now you gotta realize, if you put in the years that we actually have data for, watch, 2, 4, 6, 8, and 10. Notice those numbers are not exactly congruent with the numbers on the data. Right? In 1992, your data doesn't say 35.2 million people, does it? I think it says 35, I believe. In 1994, it doesn't say 37.3, I think it says 38. It looks like 38. This says 39 in 1996. This says, looks like 41, and this one says 44. But you got to remember, these are the data values the model is predicting. Remember, it's a best fit line, not a what? Good. I was thinking perfect fit, Joanne, but yeah, it's not going to give you the actual data. It's going to give you the best average closest to the data. So you should expect these to be off from your actual data in general. Michelle, go ahead.
I was just, because when I went through to get that table you have right there, it actually gives me figures from...
The same thing happened to Tammy. You have to set it up. You have to set it up so it does it. We'll stop at the break and I'll show you guys that. We set that up yesterday together. We'll do it at the break. Happily. Cool? Awesome. Great. And that's as far as we got yesterday. So let's move on now. And then we can get some new data because I sense you're getting bored.